Okay, everybody, just a short lesson on some other yield measures other than the yield to maturity. The yield to maturity is by far the most important one, but you need to know a few more, and a look back at some of the conventions that we apply, especially when computing things like flat price, full price, accrued interest. So I'm going to start off with something that you may indeed be examined on numerically in a quantitative question, although it's very easy to do, something known as the current yield. Now, the current yield is much simpler to compute than the YTM. It's simply the annual coupon divided by the bond price, and here it is worth mentioning that if in doubt, or if ever you need it, it's going to be the flat price, bond price. This only matters when you've got a bond price in between coupon payment dates. But typically in the questions you'll get a bond price immediately after the previous coupon has been paid. So flat price is equal to the full price anyway. So just understand that this measure ignores the frequency of coupon payments, because we take the annual coupon as it is, irrespective of how many bits it is actually split into. It completely ignores the time value of money. So this idea of interest on interest, that's not really an issue here. And it also ignores accrued interest. Hence, our focus here on the flat price. Right, a very simple calculation, a question on this. This is the same setup as you had in a previous video where we computed the YTM, the yield to maturity for the first time. Sort of the current yield for a 7-year 6.4% semi-annual coupon bond trading at 97.24 per 100 of par value. Previously we calculated the yield to maturity using this data. Now it's going to be the current yield, and that is just taking this coupons, even though it gets paid semi-annually, it's 6.4% of 100 for the full year. So it's 6.4 divided by the price, 97.24. Now I'm not going to show you necessarily my calculator. This is just too easy. 6.4 divided by 97.24. That gives 6.58%. So that would be the answer here. Nice and simple, nothing difficult about it. It's a very easy question if you get such a question in the exam. Now, more importantly, or just as importantly, let's move on to discuss some of the conventions that you need to know. We've actually introduced a few of them already. When I say conventions, I mean the way we count days and what we assume to be the number of days in the year. So you have to know about the actual by actual convention and the 30 by 360 convention. This is the one, the actual by actual, where you take the actual number of days. Remember when we were doing full price computations or dirty price computations, you were taking the value of the bond as at the end of the previous coupon payment, and then extrapolating its value, and you had to count the number of days. Well, the actual number of days from the previous coupon to the current, today's settlement date. When you do this computation, you take the actual number of days, whatever that number of days is, and also we assume the actual number of days in the year, be that 365 or perhaps 365 and 66. You can go back to those to that video on full price, flat price and accrued interest to perhaps look back at this. Now, the alternative, and that is, I believe, the one that I used in that question back in that video, is the 30 by 360 convention. This is where you take or you assume the number of days from the previous coupon payment to the settlement date is computed assuming a month equals 30 days, and of course additionally there are 360 days in the year. Now, the first convention, actual by actual, this will be typically used for government bonds. Used for government bonds. Whereas the second one is typically used for corporate bonds. Typically used for corporate securities. Okay, good. Now, the little additional thing that you need to know about, which is absolutely sort of connected to what I wrote over here, is that there is an easy way to make restatements between the yields calculated under the two conventions. So, didn't want to highlight, wanted to write, to restate. There is an approximation that you can use. Mind you, it is an approximation, but it is used. If you want to have an approximate yield computed on an actual by actual basis, starting with the yield that's been computed on a 300 by 360 basis, you need to take this one and multiply by a factor of 365 over 360. Now, I'm not going to do a numerical example with you. It's going to be very simple, right? Just take the lower number, the yield on a 30 by 360 basis, multiply by 365 divided by 360, and that should give you an approximate yield as if it were computed on an actual by actual basis. This approximation gives us what's known as the government equivalent yield. So it's not exactly the yield on an actual by actual basis, but a government equivalent yield. And you know, the name comes from the fact that it's government bonds that typically get computed using the actual by actual basis. But if you've got a corporate bond to which this rule was applied, 30 by 360, you can still check what it would be under the other convention. And that's especially useful, or it's used especially to calculate the spread, the yield spread over government bonds, used to calculate yield spread, or the yield spread over the government yield, the government bonds, right? Because in order to check how much more a corporate bond is yielding relative to a government bond, you have to get their yields to the same basis, or approximately, let's say, the same basis. So this is what it's useful for. Now, a couple more points. This is going to be a relatively short video, don't worry. How do we account for, I mean, how do we get around the problem of weekends and holidays? So accounting for weekends as well as holidays and non-trading days, that is, right? Now, this is a separate split from the one we had over here. So 30 by 360 or actual by actual is one split in terms of how we calculate yields or conventions, and then what conventions we assume, and then we've got another set of conventions. That's the street convention versus the true yield computation, which is once again the true yield. Even though it says yield, it's actually a convention. So, if a bond pays coupon semi-annually, like on the 15th of March, let's say, and then on the 15th of September every 6 months for many, many years in a row, some of those 15th of March or 15th of September dates will in fact be weekend dates or public holidays, in which case the coupon will typically be paid on the next possible trading day or working day. Under the street convention of computing yields, we don't account for that delay. So the yield is simply computed without any accounting for weekends and the delays that they cause, or holidays, right? And the delay that they cause to the coupon payment. Whereas under the true yield approach or convention, here, this one uses actual payment dates. So it takes weekends and holidays into account. Takes weekends stroke holidays absolutely into account. So if the payment happens on the next Monday, after a weekend, we will use the date for the Monday. That's what you can, for example, do in Excel using IRR to compute the yield to maturity, the formula. Now, obviously, the street convention is the simpler of the two approaches. So it's widely used in practice. This one is used less commonly, although I've seen it used, especially with government bonds, for example, where I come from. And, they're typically quite close. The computations are typically very close, so there isn't much of a difference anyway. But always, because of the possible delay here, because of the possible, the coupon actually being paid on a slightly later date than with the street convention, you should find that the yield computed under the street convention is always equal to or higher than the true yield. The true yield may, in fact, be lower. If it is, then it's only a little bit lower. You'll see that on the third point after the third place after the decimal point of the second place. So it's not going to cause a big difference. But there's always going to be this due to the fact that under the true yield, things may in fact be a little bit delayed, causing a lower rate of return or a lower yield. So the final measure here to consider is something called the simple yield. Now, I'll only really write down the formula. I haven't seen this at all examined in any numerical question, so you kind of need to know the definition. It's not even a formula. This is a computation which actually gets done in practice only realistically with Japanese government bonds. So it's going to take into account the sum of coupon payments, so the sum of the interest, plus the straight line amortization, straight line amortized, actually amortized, not amortization, straight line amortized share of gains or losses. I guess coming from the fact that you may buy a bond at a premium or a discount, and that premium or discount amortizes away. So on a straight line basis, you can compute how much of it has already amortized, and you relate this to the flat price. That's the definition of a simple yield. never examined, I haven't seen this examined numerically. However, I've seen a question in your curriculum where you just have to match the definition to the name, and this is given, and you have to match it to the definition to the name simple yield. As simple as that.